Hey, welcome to our explainer. Every single day we trust the world around us. Bridges, roads, huge buildings, and we never really think twice about it. But what actually makes all that trust possible? That's what we're digging into today. The incredible, invisible science that makes sure the very ground we build on is safe and sound. And really, it all boils down to this single, crucial question. So when you see a massive skyscraper going up or a brand new highway getting paved, how do engineers know, really know, that the ground underneath can take all that weight? The answer, it turns out, isn't just about digging and flattening things out. Nope, it's all about measurement. And the tool they use for this incredibly important job, well, it's a true unsung hero of the modern world. Seriously, you'll find it on pretty much every major construction site, but most of us have never even heard of it. Okay, so here it is. It's called a portable nuclear gauge, or PNG for short. Basically, think of it as a super high-tech tool that shoots these tiny particles into the ground to figure out how packed or compacted the soil is. And getting that measurement right is absolutely key for quality control in construction. And, this isn't some brand new, untested gadget. This technology has actually been around since the 1950s. It's been tweaked and perfected over decades to become the gold standard, really all around the world, for making sure our infrastructure starts on solid ground. All right, so how on earth do you use atoms to measure dirt? It sounds like something straight out of science fiction, right? But the physics behind it is surprisingly straightforward. And honestly, it's pretty brilliant. So here's the clever part. The gauge is actually doing two different jobs at the exact same time. First, for density, it uses a source called cesium-137. This sends out gamma rays. Now, if the soil is really dense, it kind of blocks more of those rays, so fewer of them make it back to the detector. Simple enough, right? Then for moisture, it uses something else, americium-241. This one sends out neutrons. And what's cool is that these neutrons slow way down when they bump into hydrogen atoms, the H and H2O, water. The detector just counts how many of these slowed down neutrons show up. So you've got two sources, two different measurements, all packed into one amazing device. So if you boil it all down, it's really just a simple three-step process. A little dance, if you will. 1, the gauge emits particles. 2, those particles go out and interact with the soil in a very predictable way. And 3, the detector counts whatever comes back. Then the little computer inside the gauge does the math and translates that count into a super precise density and moisture reading. That's it. Okay. Let's be honest. The word nuclear can sound, well, a little intimidating. So we have to talk about the elephant in the room, radiation. How can this thing possibly be safe to use on a busy construction site with people all around? And that is exactly the right question to be asking. While any radiation carries some risk, the answer really comes down to one thing: the dose. How much are we actually talking about? Okay, to really put that dose into perspective, let's just look at the numbers. The amount of radiation from a single 60-second test is, well, it's tiny. A trained operator, using this thing all year, might get about 10 to 20 millirums of exposure. Now compare that to a single chest X-ray, which is about 10 millirums. Or, get this, the 300 millirums we all get every year just from living on planet Earth. That's called natural background radiation. So when it's handled the right way, the risk is incredibly low. Safety really boils down to this core principle in the industry called ALARA. It stands for as low as reasonably achievable. And it follows these 3 golden rules that really you can apply to any radiation source. First, time. Spend as little time near it as possible. Second, distance. Get as far away from it as you can. And third, shielding. The gauge itself has already taken care of that part. It's got heavy lead shielding built right in. But out of all those rules, distance is your best friend. It's the most effective tool you have. Just look at this chart. You can see how fast the radiation level drops off. At just 6 feet away, that's about 2 meters, the exposure is pretty much down to the same level as the natural background radiation all around us. And that's exactly why operators just take a few steps back while the 1-minute test is running. Okay, so we've got the science down and we understand the safety rules. So let's see what this looks like when it all comes together out in the field. So out on a construction site, the whole process is actually really quick and standardized. An operator finds a good spot and smooths it out. They drill a small, narrow hole for the probe, then they just insert the source rod down to whatever depth they need to test, hit a button to start the test, and step back. 60 seconds later, boom, they have an exact, instant result. No waiting around, no sending samples off to a lab and waiting days for an answer. But what does that number on the screen actually mean? Well, the gauge gives you what's called the field dry density. That's the on-the-spot measurement. Then that number gets compared to the maximum dry density. That second number is figured out in a lab ahead of time. It's basically the absolute densest that that specific type of soil can possibly get. You divide one by the other, and what you get is the percent compaction, a simple percentage that tells the engineer exactly how good of a job the construction crew did. And right here, this is the magic number. For almost all critical infrastructure, we're talking road bases, building foundations, embankments, the engineer's specification will require at least 95% compaction. If the gauge reads anything less than that, it's a fail. They have to go back and compact the soil again until it passes. So that brings us to the final and honestly the most important question. Why? Why does that 95% matter so much? Why go through all this trouble with nuclear physics on a construction site? The answer is simple, because the stakes are incredibly high. This quote right here really says it all. When the ground isn't compacted properly, it's not a question of if something will go wrong, but when. See, poor compaction means the tiny air pockets in the soil haven't been squeezed out. So over time, the ground will naturally settle and shift, and that leads to all sorts of problems, from stuff that's just annoying, like potholes and cracks in your foundation, to much more serious issues like water seeping in and eroding the base of a road. In the absolute worst-case scenarios, it can lead to a catastrophic structural failure. So really, the next time you're driving down a perfectly smooth highway, or you use an airport, or you walk into a big, solid building, take a second to think about this little device. The portable nuclear gauge is that invisible gatekeeper, the unsung hero that confirms the ground is ready for us, making sure our world is built on a foundation that we can absolutely trust. It really makes you think, doesn't it? What other incredible, invisible science is out there, quietly working behind the scenes, just keeping our world standing and keeping us safe?